we're obviously going to talk about different types of bonding. Covalent or ionic. Covalent bonding is characteristic for molecular compounds, while ionic bonding is characteristic for ionic compounds. So first we're going to talk about ions. What ions are and what it entails. Okay, cool. So the idea is this. We have two types of ions. Positively charged, that are also called cations. This happens when they lose electron. Think about this. You lose one negative charge. Okay? When you lose one electron, not you, but an atom loses one electron, does it retain the same number of protons? Yeah. You're losing just one negative charge. But if, hypothetically, an atom of potassium, number 19, would lose one proton, what would it become? Argon, yes. I'm going to put it in your head over and over again, okay? It's all about, when we talk about charge, it's all about electrons. You get more, you're negative. You lose some, you're positive, okay? So, basically, this formation of ions allows elements to form what's called ionic compounds when positively and negatively charged ions form an ionic bond between them. Am I making sense? Yes, no? Yes, okay. So when sodium, in this case, loses an electron and chlorine acquires it, you get positively charged sodium, negatively charged chlorine. They interact strongly, so good. Now, in case of covalent bonds, electrons are not explicitly exchanged, they shared, okay, as we will see. So, first of all, there is a concept here that we didn't talk about yet. The concept of valence electrons. So we need to address this. Okay? So let's say you have a nucleus of, say, lithium. Okay, go ahead. I'm going to train this as a reflex in you, like turning your head and looking at periodic table. How many protons does this nucleus have? 3. So 3 protons. How many neutrons does this nucleus have? 4. Exactly. I'm simplifying it. How many electrons does this atom have? 3. Which period is lithium located in? 2nd. So we didn't talk about it, but basically electrons are not all circling around the atom at the same level. Okay? There are different orbitals. Do you follow my train of thought? Number of orbitals is the same as the number of the period. So if the number of the period where lithium is found is 2, it has 2 orbitals. So these 3 electrons are distributed over those 2 orbitals. Everybody follows me? We're not talking why, but there are 2 electrons on the first and 1 electron on the second. This outer orbital is valence shell or orbital, and these are valence electrons. Does that make sense? One more example, which is going to magnesium. Okay? So that's lithium, magnesium. How many protons? How many neutrons? How many orbitals? 3, because it's a third period. Okay? How many electrons? So count with me. Again, it doesn't matter why, like what, but 2 electrons on the first, 8 electrons on the second. Okay? So how many do we have left? 2. 2 plus 8 is 10, right? And then there's another 2 to get to 12. You see what I'm saying over it? Okay. How many valence electrons does magnesium have? 2. 2. These guys, right? Does that concept, crash course in orbitals, does it make sense? Sure.
So basically the group determines how many valence electrons?
Except for transition metals, yes. So actually, thank you for the comment. I'm going to put it here. So number of valence electrons equals the group number. Okay? Except for transition metals. They're just weird. Okay? So far so good? So we're talking group 1, 2. Well, okay. Actually, not quite. It does determine, but the calculations are slightly different. So look at the group 1. How many valence electrons all those elements have? That's not a complicated question. 1. Group 2. Group 13. When you start, because we skip transition metals, right? So I'm going to put groups 3 to 12, right? So we move to the group 13. How many valence electrons all those guys have? It's not 13. What do you need to do? 13 minus 10, 3. What about 14th group? How many? 14 minus 10, 4. Does that make sense? Huh? Rule. I mean, just remember the old numbering? 1A, 2A. Those would be, like group 13 would be 3A. Group 14 would be 4A. You see what I'm trying to say? Transition elements? Just ignore them. I promise I will not ask you to tell me the number of valence electrons in transition elements based on that periodic table. I can do that, like phosphorus. How many valence electrons? 5. 15. You see P? Phosphor. P. 15 minus 5. The group number. How many valence electrons for fluorine? 7. 17 minus 10. I'm going to pause right there. I'm going to take the questions now. We're going to practice with that, okay? But here's an important thing. Every atom tries to achieve the lowest possible energy. Does that make sense? I usually give this like life analogy. What is more sustainable, standing or laying down? Laying down. You're not going to fall anywhere when you already, horizontal. Am I making sense? Same idea. Lowest possible energy. Cool? Okay. And the lowest energy would be achieved if the number of valence electrons is 8. There are two exceptions.
So the number on the outside?
On the outside. Number on the inside, we don't really care. Two exceptions, hydrogen and helium. How many electrons does helium have? Total. 2. He, upper right corner. Right? 2. That's it. The first orbital can have maximum of 2. That's it. So hydrogen, how many electrons does it have? 1. How many orbitals does it have? Just 1. So this 1 electron will be on outer orbital. So it's going to have 1 valence electron, and in order to achieve nirvana, completion, it has 1 more. Because for the first I know, hydrogen and helium, the maximum is 2, not 8. Everything else, periods 2 through 7, the maximum on the outside is 8. Okay, sounds fair? So, let's not pretend that we don't know which elements we're talking about. Let's say this is sodium. How many electrons does sodium have on the outer, the valence shell? Remember the group number. Look, what is the group number? Group, not period. 1 valence electron, right? Now let's take a look at chlorine, which is number 17. Which group is it in? Group, the vertical. 17. What do we need to do with that number? What do we need to subtract? 10. So how many? 7. If you look at the image, 7, right? See that? If you want to get to, and believe me, the previous one on sodium, like the outer 1 electron, and then next one has 8. Okay? If you want to get to 8, so this is sodium. Okay? This is chlorine. If you are an atom of sodium, is it easier for you to just let 1 electron go and try to snatch 7 more? You're going to let 1 go. So you're going to lose that electron, and you're going to give it to chlorine, which already has 7. So getting 1 more isn't a big deal, right? So now, all those 8 electrons are with chlorine on the outer shell. Is it happy? It is. What about sodium? Well, it lost its outer electron, right? But the next orbital is just fine. Still happy. So this is the exchange. Covalent, sharing the electrons. So 2 chlorines. Each of them has how many electrons on the outer shell? 7. Right? 7. And you see that? 7. Now what they're going to do, they're going to take these electrons that don't have a pair, and they're going to pair them. They're going to, quote unquote, own them. They're going to be like in mutual ownership. They're going to belong to both chlorines. Does that make sense? Covalent. Okay? Does that make sense? Now we are, maybe not today, we're going to talk about, actually I'm going to finish with this, with my statement, and we're going to start from that point on Monday. But here's what I want to make a point of. So imagine you have, does anyone have a sibling? Okay. So I don't know, like, imagine my brother is 11 years older than me. When I was a kid, like 5 or 6, imagine we would have an Xbox. I would not play an Xbox because he can beat the shit out of me and he can take it to him. This is an ionic bond. This is what he did when he came back from military. Bit the shit out of him. Okay, makes sense, right? So it's his. Now imagine now we are, let's say I am 17, he's 28. He's better at it, but I can kind of kick his ass to a certain extent. So we decide he's playing 4 days, I'm playing 3. Is it fair? No. I mean, just because he's stronger, he gets to play more, right? Do we share an Xbox? Yes. Do we share it equally? No. This is a polar covalent bond. Good? Now imagine two identical twins that are physically have the same capacities. 3.5 days for one, 3.5 days for another. Right? This is the equal sharing. So in this example, this covalent bond, these two atoms are the same. They're not going to have, one is not going to have any dominance in owning those electrons. So this is nonpolar covalent bond. Does that make sense? Okay. So we're going to chat about positive ions and all other crap on Monday.